This video looks at the enormous contributions made by Georg Cantor to modern mathematics, particularly his development of set theory, the Cantor set, and his diagonal proof. Georg Cantor was born in Russia in 1845 and moved to Germany at age 11, where he lived most of his life. As a teenager, Cantor showed prodigious talent in both music as a violinist and also in mathematics. Cantor studied at numerous universities in Germany and Switzerland, attending lectures by other well-known mathematicians, including Leopold Kronecker, who would later take an active role in opposing his work. Cantor accepted a position as a lecturer at the University of Hull, where he was made full professor in 1879. In later life, Cantor suffered from severe mental illness and depression, although he continued to lecture in mathematics and even occasionally gave lectures in his other areas of interest, such as English literature and philosophy. Cantor died in 1918, aged 72. Cantor's most well-known contribution to mathematics is set theory. The value of set theory is not in its application, but in the language that it has provided for the development of all areas of modern mathematics and computer science. But Cantor's work was so much more than the development of this language. Cantor was a maverick. Set theory was simply a tool he needed to develop so that he could rigorously explore his ideas of the infinite. One outcome of this exploration was Cantor's discovery and proof that some infinities are bigger than others. Specifically, with his diagonal proof, Cantor was able to demonstrate that the set of real numbers has a higher cardinality than the set of integers, notwithstanding that each are infinite sets. Another example of Cantor's work on the infinite is the Cantor set.
So what we have here is we have a visual diagram of a Cantor set from 0 to 1. So what we do to expand that is we take out the middle part, so we split into 3 parts first. So we take out distance between 1/3 and 2/3, and now we have these 2 distances, and then we're going to do the same step to that. So we're going to take out 1/9, 2/9, 7/9, and 8/9. And then what we're going to do with that is we're going to repeat that step, so we have 4 parts now. And we repeat that step an infinite number of times. Now, what the amazing thing about Cantor sets is that even though an infinite number of points remain, the distance taken out still equals to 1, even though it's a minute and unimaginably small amount of distance.
Cantor's impact on other mathematicians during his lifetime was extremely limited, as his work was widely regarded with suspicion. Henri Poincaré, a French mathematician, stated that later generations will regard set theory as a disease. Kronecker, his former professor, actively opposed him, particularly his work on infinity, preventing him from attaining a position at the University of Berlin. Cantor corresponded with Swedish mathematician Gösta Mittag-Leffler until Mittag-Leffler asked him to withdraw a paper from his journal Acta Mathematica on the basis that it was about 100 years too soon. During his lifetime, Cantor's only ally and the first mathematician to recognise the value of his work was German mathematician Richard Dedekind. In modern mathematics, the Cantor set has been abstracted to the Cantor space and is utilised in topology. It has been particularly useful in describing the topology of fractals. A fractal is a never-ending pattern and can be found in nature and is easily generated by computer programs. Cantor's diagonal proof has also been adapted and utilised to prove many other results. For example, diagonalisation was used by Church and Turing to show that there is the same number of things that can be done as there are integers. Finally, even a novice mathematician can appreciate the impact of set theory on modern mathematics because the language of sets pervades mathematical concepts and methods, from the trivial to the complex. For this alone, Cantor's contribution to modern mathematics cannot be overstated.